This video is for number 72 of section 8.6. A space station shaped like a giant wheel has a radius of 100 meters and a moment of inertia of 5 times 10 to the 8th kilogram meters squared. A crew of 150 lives on the rim, and the station is rotating so that the crew experiences an apparent acceleration of 1g. So initially we have the wheel-shaped space station with an initial radius, r sub I, equal to 100 meters. We know the moment of inertia of the space station is equal to 5 times 10 to the 8th kilogram meters squared. And we know that 150 crew members live on the rim of the station, and they experience an acceleration equal to 1g. When 100 people move to the center of the station for a union meeting, the angular speed changes. What apparent acceleration is experienced by the managers remaining at the rim? Assume that the average mass of each inhabitant is equal to 65 kilograms. Okay, so now we just found out that 100 people moved to the center, so there are 50 left on the outside, and each inhabitant has a mass equal to 65 kilograms, and we are looking for the acceleration that they experience. So we can use the conservation of angular momentum. L sub I is equal to L sub F. The initial moment of inertia is equal to the initial angular velocity times the initial angular velocity is equal to the final moment of inertia times the final angular velocity. And we're going to use this equation to solve for the final angular velocity. But before we do that, let's determine the moment of inertia initially and finally. So our initial moment of inertia is equal to the moment of inertia of the crew plus the moment of inertia of the station. And the final moment of inertia is equal to the moment of inertia of the managers plus the moment of inertia of the station. We know that the station is wheel-shaped, so we're going to use the equation mr squared. So the initial moment of inertia is equal to 150 mr squared, because there are 150 crew members, plus the moment of inertia of the station that it gives us, and the final moment of inertia is equal to 50 mr squared, because 100 of the members went in, so there are only 50 left on the outside, plus the moment of inertia of the station. We can find the initial angular velocity using the centripetal acceleration is equal to r omega initial squared, which is equal to little g. So the initial angular velocity is equal to the square root of g over r. So when we rearrange our equation over here, we divide by the initial, or by the final moment of inertia to solve for the final angular velocity, and then plug in the equations that we know. And then we can now put in the values that we know. 150 times 65 kilograms per person times the radius of 100 meters squared plus the moment of inertia of the station, 5 times 10 to the 8th kilogram meters squared, all divided by 50 times 65 kilograms times 100 meters squared plus 5 times 10 to the 8th kilogram meters squared. And this is all multiplied by the initial angular velocity, the square root of g over r. So when you solve for the final angular velocity, with these numbers you'll have 1.12 times the square root of g over r. And the problem asks us for the final acceleration, so we can use the final centripetal acceleration is equal to the radius times the final angular velocity squared. So we have the radius is times 1.12 squared, and then when you put in the final angular velocity, square root of g over r, well, that squared is just g over r. And then these r's cross out. And you will get a final answer of 12.29 meters per second squared.